Let's just continue a little bit. Some additional considerations about heterogeneous nucleation rate, surface tension, and contact angle. This is our I theta term. What does I theta term define? It's essentially the ratio of the sphere cap to the whole sphere. And what is cosine theta? Theta is our kind of wetting angle between the solid and the mode, right? Where do we get this equation? We get it from this guy. Make sense? This is our balance of surface tension. This is our balance surface tension. We rearrange, we would get this cosine theta term. And then we would calculate the I theta term. Okay? Then, as we said earlier, if we have small sm, gamma sm, which means what? Small gamma sm means the mode likes or hates the solid. Likes, right? Small gamma sm means the mode is similar to the solid. The solid likes the mode. In that case, as we said, okay, if this term is small, we would have smaller theta. And smaller theta means smaller S theta. Remember that curve, and means faster nucleation, or the smaller barrier, faster nucleation. That's one thing. The other one is, okay, once we have a fixed mode, what about the so-called mode microstructure? You may imagine on the mode we may have local what? Micro cracks within the mode, right? Your solid is never perfect. It will have all types of micro cracks. And if we have so-called flat mode, we would have this sphere cap. And in some cases, we may have local mode goes like this, so-called convex shape. But we may also have a local mode goes like a concave shape. In all these three, what has to be fixed? So-called theta. Because theta is determined by the balance of surface tension. Make sense? But in all these three cases, concave, flat, convex, which one, to maintain the same theta, which one has the smallest cap area? If these three cases maintain the same theta between convex mode, flat mode, concave mode, which one has the smallest sphere cap volume? Concave one, right? Makes sense? So, in general, no matter what people find is, no matter what shape the local mode, the nucleation, critical nucleation energy is always the delta GV times half of that volume. So the smaller that volume, encompassed volume, the smaller the barrier. The smaller the volume, the smaller the barrier. Okay? So generally the concave one, when it's like this, or within a deep crack, that in that case we would have the smallest volume for the nucleus and the smallest barrier for it to overcome. And typically it would grow out first in these types of locations within the small cracks. Okay? And one final thing would be so-called impurity density. Impurity density. If I have more cracks, of course, I have more what? You have more cracks, I have more nucleation sites. Make sense? So adding seeds or so-called inoculants or introduce more cracks would increase the so-called nucleation rate. And when we have higher nucleation rate, another consequence is more nucleus. Each of the nucleus can grow to a smaller size. In the end, we would have smaller grain size. Okay, that's actually one way that people try to reduce the grain size by adding a lot of small seeds or make the mold surface more defective. We can reduce the grain size. Okay, so I guess let's stop here. Yeah, let's stop here. We have our meeting, right? Or you have something that you have to. You're doing synthesis? Okay. So do you want to meet tomorrow or maybe? Okay. Good. Okay. 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 So yeah, let's meet maybe tomorrow. It's okay. If it's precipitated, it's precipitated. So you mean when you add the titanium carbonate to water, it precipitates. What about when you add it to the hafnium chloride?